We'll now look at De Morgan's law for quantified statements. So the negation operation can be applied to a quantified statement, such as the negation of for all x f of x. If the domain for this variable x is the set of all birds, the predicate f of x is x can fly. This statement is just saying not every bird can fly. This is logically equivalent to the statement there exists a bird that cannot fly. So if not every single bird can fly, there has to be one that can't. So this is an example of De Morgan's law for quantified statements. Formally, the negation of for all x f of x is equivalent to there exists an x such that the negation of f of x. Similarly, let's consider the statement the negation of there exists an x such that a of x. In this case, the domain is the set of all children enrolled in a class. A of x is the predicate x is absent today. So in English, it is not true that there is a child in the class who is absent today. This is illogically equivalent to saying every child in the class is not absent today. So now we're looking at every child, so we have a for all. So this is saying that we have the equivalence. The negation of there exists an x such that p of x is equivalent to for all x, the negation of p of x. So for instance, let's negate these two statements. We'll start with the first one. The negation of a for all statement is going to transform to a there exists. That was the first rule we looked at. So we get there exists an x, and then we have to negate the predicate. When we negate, it basically means the opposite. So if x squared is not greater than x, it has to be less than or equal to. So the negation of for all x, x squared is greater than x, is equivalent to there exists an x such that x squared is less than or equal to x. When we negate a there exists, it becomes a for all. And then we also have to negate the predicate. So we change the exist to a for all, and we want to negate x squared is equal to 2. So we'll say for all x, x squared is not equal to 2.